So before we begin, a small announcement. A phone was found in one of the bathrooms. So if it's yours, please come to pick it up later. So our next speaker, we're very happy to have Erik Verlinde, also that he was able to accept the invitation on short notice. And he's going to talk about quantum detailed shockwaves near black hole horizons.
Balance, it should be. Okay. The title is indeed quantum detailed balance and shockwaves. It's actually I will motivate while we're talking about this. For me, it's kind of a special place to be now, and also to talk to Gerard here, because this is the same location where Gerard spoke to me and Herman about 34 years ago, when we had our graduation from undergraduate. So I followed the lectures here, and Gerard, that was in 1985, gave a speech first to me, and then to Herman. It was identical, because, well, we were finishing our degrees at the same time. It's also when we started our research on string theory, but the year before we had been working with Gerard also in lectures on black holes, because Gerard started being interested in this. I should have mentioned, oh yeah, the reason, by the way, we were here, actually it's a much nicer location in the center. We were here for the graduation because the center was occupied by students at the time. Don't know whether you remember if this happens in the Netherlands. Of course, we had Herman, also Robert was at the time, well, about a year later. I saw both of them in Brussels. They also want to congratulate you, and they were, well, not so happy to not here, and anyway, they had to go back to Princeton, so I'll represent them as well. Because indeed we learned about black holes, which at that time was not the usual topic to work on. It was really something, string theory has just started, and the whole problem about addressing quantum gravity from the point of view of black holes was not a usual perspective. So in that same year, Gerard published a paper on the quantum structure of black holes, and what I'll be talking about today will be very much related to what is in this paper. So I'll actually explain a little bit because it has influenced my thinking quite a bit. The motivation actually comes directly from this paper. Actually, maybe you should indeed read a little bit what is written in the abstract. He really thinks about black holes as ordinary quantum systems similar to elementary particles. And already here he talks about actually this property of detailed balance, which I will mention, and the shockwaves. So this is already in this paper, which was submitted in '84 but published in '85. And the motivation indeed is trying to understand better what really forms a black hole, but also what makes the local structure of the horizon look like it is. Because it's kind of magical that you have an inside of the horizon, and then you have this quantum state, and you would like it to evolve unitarily, and clearly there's a tension between the two. So the picture on the left is where we have a black hole viewed from the outside, where it can interact with particles, and it just emits particles, it can absorb particles, and this is the point of view that you can also think about as an atom that is radiating or absorbing radiation. If you take that point of view, you can understand how things evolve unitarily. But you don't understand how this right-hand picture of the horizon with the inside would appear from that. So that's the question I want to address, and it's very much related to current research about the question about the regularity of the horizon, or whether there's a firewall, and what has entanglement to do with this. And the approach I'm going to take will be very much motivated by, indeed, this study. So this is the picture here what they drew at the time, and actually, if you think about this, he considered, Gerard considered particle states as being discrete states with things like this, and then he realized at some moment when the energies go up, you have a very dense number of states. This, by the way, is exactly the picture we now have in ADS-CFT. This is the spectrum that we think that any theory that's dual to gravity should have. And that was already sort of motivated from this picture. And actually he argued, indeed, which at that time was not so obvious, that the black hole entropy formula of Hawking and Bekenstein should be regarded as describing the density of states. And for that argument, he used the absorption and emission of particles, and then you can derive this density of states by assuming detailed balance between emission and absorption of these particles. But then the Boltzman factors that appear there are really due to counting the genesis of states between two energy levels that are separated by an energy omega. And I think this is a really deep fact, because these Boltzman factors appear everywhere, and they appear in the local description of horizon, but if you think about it statistically, these Boltzman factors always tell you something about the density of states. So this, I think, indeed is sort of the key to understanding also where this local structure of the black hole horizon comes from, is understanding where you can find these states in that story. So this was the calculation that was indeed in that paper. You calculate the absorption and compare it to the emission. Actually, the absorption is kind of clear what the cross-section is. The cross-section is the cross-sectional area of the horizon. But if you compute it quantum mechanically, you get some expression in terms of the matrix elements of two different states of the black hole, where you have a particle outside or the particle is being absorbed. And this is the density of state of the black hole. And the other process is where you emit a particle, then you have to go from a state with energy E to a state with energy E minus omega. But the densities that you put here are different, because then you have to sum over the final states, and then you have to include some phase-space vector for the particles themselves. But detailed balance tell you already that the ratio should be determined by the thermal factor, and this is how this derive this relation, and then you can integrate this back up to derive that the density of state should be that of the black hole degeneracy, or the other way around. If you know the black holes, how much entropy they have, you can derive what is the Boltzman factor that comes from here. But the Boltzman factor is always written as this ratio. And so it appears from statistical properties of the density of states. And I want to emphasize that again, because I think that's really, if we study thermodynamics in textbooks, this is also how we motivate the canonical ensemble, by first thinking about density of states, and the temperature is defined in terms of that. But this is not the way that you can derive it in the local description of horizons. You do it from properties of fields in the near vacuum of this black hole, and it's some analytic properties of the field operators, or the fact that if you impose that there are only positive frequency mode locally, that the analytic property gives you these Boltzman factors. So what do these two stories have to do with each other? Indeed, locally the state looks like what's now called the thermal field double state. It satisfies certain properties, but here we have to assume some interior operators that are describing particles behind the black hole. And of course, they are not part of the original story, because we're talking about first just the perspective of having particles on the outside. So where do these inside operators come from? And as I mentioned, this question became more urgent because of a firewall paradox, which had to do with understanding the entanglement structure near the horizon in comparison also to the entanglement with the early radiation. There's another way to understand this Boltzman factor, which is by this analytic continuation, and I'll point that out here too. Namely, it's by thinking about Euclidean picture, and this is indeed when you do analytic continuation, you go to Euclidean, and then you can think about the two sides of the horizon as taking the Euclidean black hole and doing half a rotation around of an analytic continuation halfway around the thermal circle. So instead of going all the way around, which is like shifting things by I beta the time, but now you do it halfway, and this is sort of how you end up in this thermal field double state. And this is also how you explain these funny half Boltzman factors. But it's indeed the other side of the horizon just actually appears from an analytic continuation. I regard this as a trick. I don't think there's reality to it. I think the other picture that I was describing is much more real, because it's a thermal situation where you indeed can understand the thermal equilibrium. This is the picture that arises from it, and I want to understand how that arises. So this is indeed the question I want to ask, is how does, from a picture like that, we arrive at a picture like that? And the idea is indeed that here the Boltzman factor comes from statistical counting of states, while here it's sort of an analytic continuation of some Euclidean solution or something in geometry that we're doing here, assuming a local vacuum state. Because these states are statistical in nature. You don't encounter Boltzman factors just like this, and actually the detailed balance calculation actually shows you this. Because in order to establish detailed balance, you have to compute transitions between states and sum over many states. There's a certain force grain required to get these kind of Boltzmann factors. So what is the intuition? First of all, the intuition is that there is an interaction required. If you want to have a system that thermalizes with a heat bath, then as we take the analogy with the atom very seriously, there's a probability of emitting particles and absorbing particles, and that equilibrium tells you what is the occupation of the states on the outside, but also how the density of states gets imprinted in the distribution of the spectrum on the outside. So understanding the microscopic interactions between the particles on the outside spectrum and the states of the black hole are important. And so this is the intuition, basically modeled after what we do in atomic physics. We make transitions between particle states, and there we take actually a window of states, because we don't take just one size energy eigenstates. We have to have a certain width, because this is how we're going to end up with the degeneracy, well, the density of states. We have an interaction Hamiltonian that can create particles on the outside, or it can annihilate them. But at the same time, because energy is conserved, it has to make a transition inside the internal states of the object that I'm looking at. So when I act once with this operator, I'm creating a particle, but at the same time I'm doing something with the state internal. But this picture is actually the Hawking process, where you create a particle and an antiparticle near the horizon. So this tells to me that actually the interaction Hamiltonian should know something about the process of how particles are being created near the Hamiltonian, or near the horizon, and actually also tells me something about how we should think about the operators on the other side. They should be read off from the interaction Hamiltonian. This is the intuition that I had immediately after the firewall argument, and this was the starting point of the paper that I wrote at the time with Herman on what's called quantum error correction, because actually the question of how to figure out what is the thing that's entangled with a particle that's being emitted is actually a problem that also occurs in quantum computing, and I'll come back to that at the end. So I'll make actually comment a bit about the calculation that is required to find the thermal state, because there's a lot of approximations required to do so. And actually the Fermi golden rule sort of plays an important role in this, and I had to go back to the books how to derive it, because there's something funny about the Fermi golden rule that I would like to sort of point out. So you calculate when you have interactions with a system and a heat bath or atoms that are emitting particles, you have to calculate the transition amplitudes by solving the Schrödinger equation with the interaction Hamiltonian, and not just in first order. You have to really solve it in some range of a certain amount of time, because then when you square the amplitude, you get something that can be approximated. Actually, this is an approximation where you take the interaction Hamiltonian, because actually the energies appear in here. But the reason why it's a good approximation is that if you take the time step to be very small, then indeed things can be made sort of, well, you need not to go to very high order, but you still need to go to second order at least. And you already noticed this because there's always a square of the interaction Hamiltonian in here. Well, if you would solve the Schrödinger equation, you would actually generally go linearly in the interaction Hamiltonian. So where does this single power of delta t come from? That has to do with, indeed, that I'm counting, actually summing over all energy states to which I can go. The density of states is here. And indeed, this integrand actually goes like delta t squared, if delta t is small. The reason why the result is like delta t is because this sinc function squared actually has a width that is of order delta t, 1 over delta t. So if I do the integral over the energies, I get an additional power of 1 over delta t, and this is how I end up with something that's going to be linear in delta t, and also explains why in the probabilities I always get the square of an amplitude. Anyway, this is textbook stuff, but it's something that is good to remind you of. Actually, in this step, already made some use of this detailed balance relations to give us indeed the probabilities. And I just wanted to point out indeed that if you do the quantum calculation, then with the detailed balance, you get these Boltzman factors, but they do come from the differences in density of states. So this is the calculation for the probability that I'll use later as well. But the only way this Boltzmann factor, by the way, appears is because indeed there's an asymmetry between going up or down, and that's only coming from these degeneracies. If I would do it microscopically, reversing the energies E and E prime would not change anything, because these operators generally are, the interaction Hamiltonian at least is Hermitian. And these matrix elements are symmetric when you square them. So now I want to do this in the context actually of ADS-CFT. Maybe I should have already mentioned this. Actually, this picture can only make sense if we put, of course, the black hole in a box. Otherwise, the states of a black hole have no real meaning, because it's an unstable state and there's no equilibrium. So putting this actually in ADS is a very natural thing to do, because ADS works like a box. And there we do know that this spectrum can be defined in a proper way. So this is the reason why we've been studying this in ADS-CFT. And here I have to emphasize that in ADS-CFT there's no real easy way to describe the particles on the outside separately from the states of the black hole. There's one Hilbert space that describes both of them. So we're going to be looking at states of the combined system of particles and the black hole together. And we call these typical states. So these states can be thought of as being states of microscopic black holes, but also with particles on the outside. And the transitions then happen sort of at equal energy, in the sense that we'll have to work with the operators that create the particles also on these states themselves. Now this is a typical pure state where I sum over a certain energy window with a certain width delta E. The number of those states is given by this density of states. And the typical states must have amplitudes where these coefficients are of the order of 1 over square root of n. So they're all equally large, except the phases are random. So if you then randomize over the phases, actually you end up with something that looks like a mixed state, but it's a unit density matrix on the same energy window. This is a mixed state, and actually many of the properties of the typical states and of these mixed states will be the same. There's also the thermal state where you introduce a temperature, but that temperature, of course, is something that has to be derived from the density of states. And then the eigenstate thermalization hypothesis tells you that for certain coarse-grained operators, the expectation values of all of these ensembles, basically these states, are basically the same. I can calculate expectation values in these typical states. They look like this mixed state, because basically the phase is sort of randomized. Then there's also the property that it may look thermal. Again, the temperature is sort of then derived from the energy. I will denote this by O. So I don't even care which of these points of view I'm going to take. I'm actually going to be interested indeed in understanding where this near horizon geometry sort of comes from this perspective. So I'm going to put in operators here, and actually going to think about operators which are products of the operators that create particles and their conjugates. Because I'm going to construct indeed the inside using only those operators on the outside. So actually I'm going to argue here that there is an inside if you think about it this way. Although at the end maybe we're going to remove it again. Because how do I get an inside? Actually, I make use of a construction called the GNS construction after Gelfand, Nijmeijer, and Siegel. They basically tell you if you have an operator algebra. So in the CFT, we don't have really factorization of the Hilbert space of inside and outside. So what I need to do is construct a Hilbert space. Well, sometimes it's called the code subspace, but actually there's a formal construction that doesn't even require that I start from a pure state, from which I can construct states associated with every algebra element A. I should have mentioned actually for A, I don't really mean single and creation and annihilation operator. This can be any string of operators that creates many of these particles. And omega for me just stands for the total energy of those particles. So even the relations I wrote down for the vacuum state actually are valid in that context. So I'm going to associate with these operators. I call them A and A dagger because to emphasize the fact that I don't have a real vacuum state. So that means that if I act with these operators, they generally will not annihilate the state. And I will get the basis for all of these operators. And this is due to the entanglement in this system. And so these people, they actually define an inner product by only knowing the two-point function. And that two-point function was defined here. Actually, it's where I insert indeed a product of two operators. And I just declare that to be the inner product of these states. And so it's a formal construction that actually helps you to construct a larger Hilbert space where we can indeed not only talk about particles on the outside. It turns out that this Hilbert space also knows about the particles on the inside. This algebra forms a representation, so these states, form a representation of this algebra. I can act namely with a new operator acting on these states, and the way it acts is simply by multiplying the operator on the inside from the left. And in particular, I have an identity where if I act with A on it, I get the state A omega. And you can think about this indeed, as I said, a formal purification of, say, if I start with a mixed state, I can still write it as an expectation value, the operators as an expectation value in this space. Now, this Hilbert space can be constructed inside the CFT Hilbert space if we are dealing with a typical pure state, but it can also be constructed if we are dealing with density matrices, and all the properties will still be the same. There's something indeed that you can define in this framework. It's called where you have quantum entanglement. Namely, I can look at this representation, this Hilbert space, as a representation of this algebra. And it turns out that when you have entanglement, this representation is not reducible. It is not irreducible, it's reducible. It can be decomposed in irreducible representations. And so in particular, my state 1 can be decomposed. And since they're irreducible, actually I'm going to write it as like a density matrix. I mean, there are certain coefficients that are obtained from this object that I call probabilities that tell me what is the probability that if I am in this state that I end up in one of these irreducible representations. And the fact that they're irreducible, but that the state itself was not irreducible but reducible actually leads to entanglement, because from these probabilities I can extract an entanglement entropy, and this is the generic situation when you have a thermal state. Actually, in that case, when you start from this thermal situation, this will be precisely this thermal field double state. So I've constructed algebraically the thermal field double from just the operators on the outside. What I've explained is actually a more fancy version of what Papadodimas and Raju also did a while ago, also in trying to solve the information for the firewall paradox, and I'll come back to that in a minute. Actually, a beautiful discussion of this whole construction is in the review by Klaas Landsman, who's here, and Chris van Weert from a long time ago, where they also explained indeed how to do this in a thermal situation quite formally, and they also describe how to define some dual construction, actually using the same ideas of Papadodimas Raju, which is called the Tomita-Takazaki theory. I'm not going to actually enter in this, but I'm going to tell you just formally, if I have a thermal situation, I can define another representation on the same Hilbert space, namely by acting again with operators that I call mirror operators, but they act precisely as the way that the vacuum state conditions look like, but they multiply the operators on the right with a dagger. And you can figure out that if I do it this way, I have another representation of the same algebra, but it commutes with the one that I had before. So there are indeed two representations of the same algebra, and this is how this horizon appears, simply from the thermalization of my algebra there is a purification that tells you that there must be two algebras commuting, and then the horizon appears. But this construction, of course, has nothing more than just the original microscopic picture behind it. Because I have to understand how this thermal picture arises from the interactions between the algebra and its V-class. I have no time to go through the details there. I'll tell you a little bit what we're doing. Actually, I should have mentioned I'm doing this together with one of our students. Actually, he's going to be a postdoc soon in the US, Sagar Logande, who indeed pointed out this idea of using the GNS construction. And we also came to the idea of using sort of a picture of thermalization. As I said, I have no full time to go into the details. One way that happens when you have probabilities or a density matrix is that if you are not in the equilibrium situation, so when you're not in the thermal state, there's a way to get to thermal state by a time evolution that tells you that the probabilities decode between these states actually tell you how these probabilities will change. So if these objects satisfy detailed balance, that means that there's a Boltzman factor appearing in their magnitudes, then the fixed point will be the thermal state. So this is a way of describing the thermalization or the approach to equilibrium. Actually, to derive these equations, you have to assume some Markov properties, and actually you make use of this Fermi golden rule to do so. And the same way you can actually derive a quantum version of this equation, because I can write it in terms of how the density matrix evolves, and this is called the Lindblad equation. And these operators are then the jump operators that generate transitions between different states. And I actually believe that these operators will eventually play a role in understanding also what the internal process looks like. So this whole GNS construction is kind of formal, but you have to understand how it arises microscopically and how it's embedded in the bigger Hilbert space. And then these equations will play a role. I will again not go into the details there. I just want to mention indeed the work I did with Kyriakos Papadodimos, Jan de Boer, Sagar Logande, and Erik van Breukelen. We actually did apply the same ideas using the prescription of Papadodimos regime, and actually arrived at very similar conclusions, that there is a mirror construction, and this equation is basically the same as I wrote down. And as I promised, I'm also going to tell you something about the quantum error correcting picture. So, so far what I've told you reconstructs everything as if it's just normal quantum field theory on curved space-time. But the dynamics is much more complicated. I mean, if you really think about what's going on microscopically, lots of things are happening near the horizon. And that was indeed already pointed out by Gerard in this paper. This is actually figures from that paper. He talks about shockwaves, and he even collides shockwaves in the interior from the left and the right, and sort of argues that the local geometry, from the point of view from sort of these interactions between left and right movers, sort of should come from, well, this kind of picture. And what it actually tells you is that these operators that I constructed on the interior, you have to be careful indeed in how to treat them, in particular when you start looking at large time separations or large boosts. So I'm going to actually finish with some reminding you of some development that took place recently that makes use of these shockwaves, and which I'd like to implement also in the story that I've been just telling you. This has to do indeed with the way that shockwaves actually appeared in trying to make wormholes traversable. That's actually due to Gao, De Beers, and Wall idea, where they use shockwaves to make particles actually go through one of those black holes actually in ADS space. Normally they have a throat. You can think about this time slice. Indeed, that's the Euclidean slice of the, actually it's the t=0 slice that also is shared with the Euclidean solution of a black hole here. But normally if you would evolve a time upwards here, the black hole throat will collapse and there's no way to pass through. I mean, this is the reason why there's a singularity and that this point is not causally connected to that point. But using these shockwaves that Gerard first introduced, actually, you can make a particle go through, and it has to be a special shockwave that makes actually the particle go backwards in time. But this can be implemented indeed in this context by connecting the two sides. And this is a picture of it. Actually, what you're doing is quantum information theoretically. Actually, you're doing making use of the entanglement in this situation by implementing something like a quantum teleportation protocol, and that stabilizes these wormholes. And actually, Juana and collaborators have shown that you can make even something like this really using just standard model physics well, using some stabilization of these wormholes and make them traversable in real or physical language. I don't want to go too much in the detail of these shockwave interactions, but I just want to mention indeed, in order to sort of emphasize that there is indeed some reality to the inside of this black hole horizon, we indeed make use of these shockwave pictures by saying, well, let's think about a particle that's on the other side of the horizon. I want to prove that it's there by seeing it come out. And I can do this by taking a particle going in and need to create some shockwave that allows the particle to come out. And this actually can be demonstrated by computing these kind of commutators. And actually this can be formalized even in the context of this GNS Hilbert space. Actually it's a commutator that involves the operators on the outside as well as the inside. And there's some way that these operators change the order of the time. And that's indeed, these commutators are the result of these shockwave interactions. I think I want to skip this a little bit. At least there's some more complicated full story where you want to indeed understand how does the particle really get out, because it really gets thrown into the black hole where it gets mixed with all the microscopic states. So how can I eventually see it coming out? There's some way that scrambling and unscrambling happens. And actually I do think that this same interaction is described by the interaction Hamiltonian that I wrote down. And this is an idea I want to close with. And actually I also want to come to the idea that Gerard has been emphasizing that maybe there's no interior to a black hole. So how would that be realized in such a framework? And I have an idea about this. Actually I thought about this last week. And that goes back to the idea that Herman and I sort of tried, where we thought about the black hole really as a quantum computer. So what is really the problem? What a quantum computer wants to do is you have certain quantum states inside the quantum computer that you want to protect and not be, well, destroyed by entanglement. For instance, if I have a computation I'm doing here by manipulating that quantum state, something may happen, namely the quantum computer may emit a particle. And that particle actually will create an operator acting on my quantum state. And the problem is that the quantum state that I'm ending up with will be entangled with that particle. So how do you get rid of this? And actually, how do I figure out what operator actually happened here? So you need to know the interaction Hamiltonian, and then you can undo this. You can actually make this particle not being entangled with the quantum state inside the black hole, but there's a way to transfer it to something else. So what happened due to the emission was that this factorized state, which is a pure state inside with a vacuum state on the outside, became entangled. There's actually some here which I didn't write down, but this operator and that operator, they know about each other, and therefore there's an entanglement in here with something on the outside. But there is a recovery you can do on the inside that takes this entanglement and puts it somewhere else. So that's a picture that what you need is doing quantum error correction. And so quantum error correction is some idea that I'm going to explain now as follows. It's a bit of a cartoon, but I'm going to actually think about a different Hamiltonian where I use the same operators with their conjugates, but I couple them to another particle. Of course, this particle that was emitted has gone, so I cannot really use that anymore, but I can use something that's called an ancilla as some particle, which I now denote with these tildes. And then this operator has a property, and it actually has a property because of random matrix properties that it can be inverted. If you multiply these matrices, they are basically each other's inverse if they are each other's conjugates, and so you can recover the state. But what you have done is then actually take the entanglement that was first with the quantum computer and gave it to something else on the other side. So then you end up indeed again with this would be an unentangled state. There's a state here, and this is the entanglement that actually is contained only in the particles on the outside. So suppose a black hole would exist, and the black hole would think of the following. Erik has proposed that black holes don't have an interior, but they have an entanglement which is antipodal. And I do think that this might be a way of implementing it, that maybe the black hole doesn't really entangle something with its inside, but really makes it impossible to entangle with the inside, but just transfers it to the other side of the black hole. If that is the case, there would be no inside of a black hole, because nothing is entangled with it. It's really the other side that you're entangled with. And that picture might actually work and even be consistent with everything I talked about. You don't need the inside of the black hole, but the entanglement may be transferred to the other side. And that might be actually, if you really think about what the black hole likes to do, it really likes to shield everything that's on the inside, and this is what it should do in order to avoid being entangled with the radiation or any other particles on the outside. So that might actually be a way of connecting all of these ideas together. Anyway, I go back to the question I asked. I don't think I fully solved it. I mean, we're still sort of in the process, but I think the idea of trying to explain these Boltzman factors by thinking about the density of states is a very important one. And actually, as Ted already emphasized, this question is not just about black holes. It's about what space-time looks like even locally. Because this question is really how does space-time arise? And these states that I'm talking about might actually play a role even in pictures like Winkler space and so on, or in cosmological setting. And I think that is an important question there for to solve. So I want to end here.
Thank you very much. We have time for questions or comments. Good, there are several.
I know that in quantum mechanics often Hilbert space is used, and mostly, at least, Hilbert himself invented separable Hilbert spaces. And later came on Gelfand and all others that also made non-separable Hilbert spaces. Now you can embed a separable Hilbert space into a non-separable Hilbert space. And the eigenspaces in a separable Hilbert space are counted.
I mean, you're going outside of my area of expertise.
Oh,
so what's the question?
Well, the universe is stored in a non-separable Hilbert space, in an eigenspace of a normal operator in
I think I already emphasized you're going out of my area of expertise. So
it's continuum. And
what's the question?
The black hole is probably an eigenspace in the separable Hilbert space, but which is not a continuum.
I don't know all of this. Sorry. And I didn't hear a question also.
Was there a question over there?
Yeah, I find myself wondering, so it's very hard for me to imagine that there's no black hole interior, but I wonder if it's possible that it's nevertheless true that there's an antipodal identification map of, that sounds impossible because it would be like information being located in two places, but actually I believe that's probably exactly right, that the factorization of Hilbert space that we assume without gravity theory just isn't applying, and that the way quantum gravity information is stored is more subtle. So I want to ask you, is that conceivable to you? Could it be not either or, but both? Could there be an interior?
So I think when you fall into the black hole, it will look like that you fall into a black hole. That's precisely the point that Herman and I want to show. But if you look from the outside, that may not be what happens. You may just appear on the other side. But your experience may still be the same. So black hole complementarity still fully works. What I try to emphasize is that the inside is really a thing that follows from the entanglement, and it's a trick that we've applied by an analytic continuation. GR is very good at doing these analytic continuations, but if you ask what quantum mechanically happens, I've just exchanged my algebra with whatever it was entangled with. So when I entangle one side of the black hole with the other side, this trick will reconstruct the inside, but the operators you're using are actually the ones on the other side. But from your perspective, you would not know. So I think the entanglement is what defines the trick, and actually it's how the continuation works, but there's no a priori geometric meaning, because the geometry actually arises from the quantum structure that I had. And so the inside, my idea is that even points in normal space-time are really just points where we have antipodal entanglement. So when I move through space-time, I will always be antipodally entangled. So when a black hole appears, it makes it only a little bit bigger, but you still will go through, and it will shield whatever information has been sort of in there by this quantum error correcting mechanism, where it transmits the entanglement directly to the other side. And so it doesn't allow any entanglement across the horizon. It would be another way of solving the firewall paradox, because you don't need that entanglement even to have the smooth horizon. The experience is smooth, but there's no inside.
I'm speechless.
So did you mean literally that something comes in from one side of the black hole here, and the entanglement comes out? Something entangled is on antipodally.
So the thing I tried to emphasize, this is indeed the effective description, but if you ask what microscopically happens, is that indeed the Hamiltonian initially creates an entanglement with the black hole, but then the black hole recovers it and puts the entanglement on the other side. And then you're no entanglement with the inside anymore. And there must be some scrambling that's happening at the same time, or maybe some de-scrambling at the other time, because these operations actually are almost each other's inverse. And indeed, you might end up on the other side. But actually, I wonder whether it's just a simple antipodal identification. Any sort of there's some other Z2 identification, which can be much more complicated, that may actually work. In that case, you would sort of end up sort of scrambled on the other side.
If you shoot a bullet into a punching bag,
Yeah.
then the Soft theorem says that you would get a cloud of soft gravitons coming out the antipodal sound. Is that related?
I think it is, but so actually your point has been that maybe we can understand all of this by not going to very Planckian physics, but maybe from a low energy sort of soft graviton picture. Maybe.
Well, I wasn't trying to get, but I was just wondering if that could be the thing that.
I mean, it's certainly a hint, maybe. I don't know. Yeah.
Questions there? No, that's over there. Okay, ready?
All right, just for clarification, so you apply the GNS construction to the observables of the world outside the horizon, and then the mathematics gives you a doubling of say, new degrees of freedom, which you regard as physical or as unphysical. So these still-the operators, as we call them, are they physically real for you, or?
They are complicated. Actually, they're made to look. I'm missing the word. I mean, it's as I said, it's a trick. So
yes.
These operators, actually, the whole thermal field double is a trick.
Sure.
And so these operators are actually a representation of whatever the algebra was entangled with. And finding those things is really what this quantum error correction thing is about. And with quantum error correction, you can even transfer it to something else again. And so whatever it is, it can also be a dynamical thing. So when the thermalization happens, or even when this Hilbert space starts evolving, whatever was that mirror operator is not one operator. It will be a time-dependent thing, and it will change. It will be a very complicated thing. And this is sort of going also to that question. I don't think that the other side really exists. It's a mathematical trick that sort of came from the analytic continuation. And that analytic continuation can be understood microscopically from the way that the state thermalizes, and this interaction Hamiltonian should sort of contain that.
So is this mathematical trick a reflection of your opinion that the interior doesn't exist in a way? That
Yes.
matches
Yes, but
the idea that it's a mathematical trick?
Yes, but I think when you fall in, your modes will be transferred by the Hamiltonian into those modes, and this is the way that scrambling happens.
Alright.
Someone pumps the zone, or someone being called here.
So, is the other side of this room a mathematical trick?
As I say, the point is that when you enter it, you will you can of course define your operators with the A tildes on the other side, but I would call indeed the way that it appears from one side, I mean that's the low energy description. What I make clear actually is that the local structure of the Rindler horizon can only appear through coarse graining.
I guess I was just trying to understand that your use of the word mathematical trick. Do you think that the other side of this room is a mathematical trick? Or
So
is it a mathematical trick in the sense you are discussing?
you and I both know that we're trying to answer questions about the fundamental properties of space-time and not about the low-energy physics that's happening on this space-time. I claim that the physics that's happening on this space-time, those two worlds are real. The question is, what does it mean microscopically? And so if we want to ask questions, the fundamental questions that you and I both are thinking about, I claim in that world, it's a trick. And that I think is an important thing. So the point is that one thing that I'm trying to make, and actually the question that Klaas asked, the low energy field theory, which is a GNS construction which has two things, is embedded. You may actually wonder how it's embedded in the microscopic Hilbert space. That's a complicated question. And I claim that the way that our low energy field theory is embedded in the microscopic Hilbert space of the theory of the space-time here is a complicated question, and they actually depend on the time. And therefore, the way we have derived our low energy physics, from that point of view, should be viewed as a mathematical trick.
Let's see, are there follow-ups to the question?
If I may, just a comment, a general comment, very short. It seems to me that by taking seriously an hypothesis, you and a lot of people are led to a kind of physics which seems implausible to a number of people we see from the direction. This hypothesis is that the total number of states a black hole can this hypothesis is that the Bekenstein entropy, the area, counts the total number of states that a black hole can have as opposite to the surface state. If to the surface state, as opposite to the ones which are relevant for determining interaction with outside. I just want to observe that all the strange consequences they're describing, we have heard in other, all come from this hypothesis, which is an hypothesis and might be and is not supported by just GR and quantum mechanics. Just want to point this out. There could be other degrees of freedom which inside the black hole, which do not affect directly the external, and such that at low area they are not bounded in number by the area itself.
That is possible. Anyway, I've taken this formula actually from Claire's paper seriously. This is the starting point that I started from. And there we do postulate the existence of certain states, and we exactly know how many there are, also because of the temperature that we have given them. And so these are the states that interact with the external type, as you say, because that's also how we understand that the temperature appears. And I think in that sense it's totally a consistent picture.
I think I have a question that will be the final question for this session.
Yeah, I will use a little bit of time of my own lecture to explain a little bit my attitude here. But there's one thing which I think must be a misunderstanding. When you talk about inside states, but you're not talking about the states outside the black hole, that's to say the states outside the horizon. Because if you count how many states are there outside the horizon, you find not only that that is more than you need, it's infinite, it's divergent. So outside the horizon, at the temperature T that you think Hawking radiation is supposed to have, you already have far more particle states than you want. So you don't want anything at the inside.
Well, this goes also to the question of the cutoff and how that curve appears, and how far can we trust the outside picture.
Yeah, so the simple calculation which
The
I
brick
did was the brick wall.
Brick wall.
Assume that the particles that form the black hole states are outside the brick wall, and you can calculate how far does the brick wall have to be. But that's an artifact, of course. But already that calculation gives you far more states than you really want.
Yeah, when I talked about this algebra, I actually had in mind making it small enough so that it doesn't compare to the full black hole.
But how do you make it small enough? Because it's divergent, it's infinite. So if you do nothing to cut it off, you do something
I
wrong.
have to understand, you're right, that some stretched horizon or something like that has to be introduced.
Okay, we'll leave it here. Thank you very much, Erik, for this thought-provoking debate.